Gary Macron from Ocean State Signal. Due to COVID-19, we figured we would do some online training to try to get everybody up to speed on programming the Siemens controller. We get a lot of questions about this all the time. It's a little bit of a different layout, so we figured we'd take advantage of this time and go through some of the programming. We've broken this down into a 4-part series. We're going to do them every Tuesday. Last Tuesday was part 1. We went over utilities and phase data. Today we're going to get through unit data coordination, and then we'll do the rest over the next couple of weeks. We've muted everybody just so we don't get any of the feedback. There should be a little microphone icon. If you guys want to ask a question, you can click on that, ask the question, and then just remember to click off it when you're done. If you can't do that, there's a toolbar that has a chat box. You can type your message in. We'll get the message here and repeat them. I will get the question here and repeat it. Or if all else fails, I got my phone right next to me. You can text it to me and we'll do it that way. For those that don't have my number, I gave it out last week, 401-524-3984. Shoot me a text with a question. Okay. Same format as last week. I got the whiteboard. I've modified it a little bit, but I do have some stuff left over because we're going to do the ring structure. And then also, we're doing what we call a telnet session where I'm plugged directly into the front panel of an M60 controller. So this is what you would look like if you were programming it for yourself, so we can follow along that way. A couple of things right out of the gate. Like I said, last week went well. I sent everybody a video of the training so you can go back and review it, or if you missed it, hopefully you watched it. So we're going to be able to tape all these and eventually we'll put them on the website. All right, so we'll get going. A couple of follow-ups. Look at that, I got a question right away. Not a question. Everybody's busy, so it's a good thing with everything going on with COVID-19, especially in Massachusetts. You guys are getting hit pretty hard. A lot of people out working today. That's a good sign. Just hopefully everybody's being safe. Rhode Island, we don't have it as bad. We're supposed to be reopening some stuff on this weekend, so hopefully we're going in the right direction. Okay, just a follow up from last week. 2 things I wanted to cover, a couple of similar questions, and then something that I wanted to just go over because I reviewed the whole video to see what I was doing wrong and make sure that all my information was accurate. So 2 things I want to cover right here. Both have to do with detection. If we go into the detection screen and I go in, one was with delays. So if I go into a delay, let me go this way. Three, 7. Right. There was a question about doing delays in the controller for your loop detectors. So if you remember, our example was a right turn loop right here. Okay. I'm going to close that little window. Hold on a second. Okay. So remember, we had the right-hand loop over there. So if you wanted to put a delay on that, so people making a right-hand turn, they pull up on the loop, and if they're going to make a free right turn, then we don't want the phase to come in. So we put in what we call a delay, like a 5 or an 8-second delay. So basically what happens is the car goes up on the loop, it times out 5 seconds before it puts in the present call to the controller. If he leaves, then it doesn't put the call into the controller. All right? 2 different ways of doing that.
I'm not seeing your black box.
All right, 2 people do that. All right, hold on. I'm being told you're not seeing my black box. Any idea why?
You might just be sharing that monitor, that screen, instead of sharing your desktop.
Okay.
And then share screen or share desktop, and then.
Nope. Hold on.
Looks like we shared application instead of desktop.
What happened to the TV? What happened to the monitor?
Because you shared the application, not your desktop. You want to share the whole desktop so you see everything on it. So stop sharing and then.
Hold on, bear with me. So that's sharing. You got it now?
Just use this one right here.
Yeah, but it's not coming up on me. So I'm pulling up everybody else.
Bring it. No. Yeah. No. Click that. Yep. Click there.
Yep.
Click.
Desktop.
Yeah.
Yes.
Yes. I think it's just showing the last thing you saw.
All right, well, bear with me, folks.
Here we go. You just make that. You're good now.
All right. Everybody can see the desktop? All right, we're good to go. Sorry about that. Okay. So what I was saying is, so here's our delay right here. We have 5-second delay on it. A car pulls up, doesn't input a call for 5 seconds. He takes that free right turn. If he sits on it, then it inputs the present call to the controller. All right. That varies between TS1 and TS2. So when I say TS1, that's the type of controller, the type of control cabinet that we're using. So TS1 is the older style where you have all the wiring in the back panel. TS2 is the newer style where you have BIUs and you have the SDLC bus. So if you look at this screen right here, in a TS1 controller, we don't change this, okay? These are our vehicle assignments, 1 through 8, and we have it programmed 1 through 8. So if I was to go in and put a delay, so this brings up channel 8. Well,
Can you minimize this?
this?
Yeah, it's a little back part.
Better?
Perfect.
Okay. So if I come in and I put a 5-second delay here, gotta put enter. If I put a 5-second delay like that, what that's doing, if we're in TS1, that's putting a delay on everything in phase 8. So if I had multiple lanes here, so if this was an 8, and there was a loop here, I'd be delaying both loops. Because TS1, we can't put the delay in the controller. What we have to do, I got a little bit of props here, is typically in TS1, we have loop harnesses, right? Loop harness plugs into the shelf mount loop detector. And if you see on the front of that, if I can get it up close enough, you'll see those blue dip switches. Those dip switches are delay and extend functions. So in TS1, I have to put the delay into the actual amplifier. If it's a rack style, then I have to put it on, you'll see the little delay, you'll see the little dip switches over there. So in TS1, I have to delay the channel, because we're gonna get into channels and phases today, the channel that the loop detector is coming out of. If we were in TS2 land, now we program, because we're going through the SDLC bus, now we program our delays in the controller in the channel. So it would look more like this. This would be, I'm just going to go through real quick. So when you go into a TS2 controller that has the BIUs, it has the SDLC. When you go into your detector assignment, we now manipulate the programming of the vehicle assignment. So you'll notice that it goes 1, 6, and then typically it'll go, this would go 5 and then 2. Basically, it'll be representative of all my phases that I have here. So because we have channels in here, this is where I put my delay in. So in TS1, we put our delays onto the device, on the detection device, the shelf mount loop amp, the rack mount loop amp. In TS2, we put it into the controller. So hopefully that clarified that a little bit. Just put this back where it was. All right. Now the other thing that we had a little bit of confusion on was, I'm just going to go through the recalls again real quick. Basically the 3 recalls that we had: min recall, max recall, and soft recall. Min recall, pretty standard. I think we covered that. You put the controller in min recall, and we're going to time the minimum green. Let me just get to it real quick. All right, so I'm in min recall right now. You see the little R's. If you look to the left, where it says ring 1, ring 2, you'll see that it counts down the minimum green. Right? It's max timing in the bottom, but you'll see the min green counting down 2, 1, and then it's going to drop out and change. Right? If I change that to max, I'm on 2 and 6. We're going to time down that max timer down below. So we're just going to get out of it. We're going to go to 2 and 6. So now we're timing out that max timer down below. So there's your difference between min and max recall. Where we had the issue with, I didn't demonstrate soft recall very good, is if we have soft recall on the main line, which is very common. Right? So I got soft recall on 2 and 6. And again, I spoke to that like it was a placeholder. When we don't have any calls anywhere else, soft recall places the call so we can rest in green somewhere. So right now we're resting in green. I have a peer function going on right now. Let me get that out of there. Hold on. Doing 3 things at once there. All right, sorry about that. That'll go away. That's for some of the peer-to-peer that we're going to be doing here in a minute. So I go into what I was trying to demonstrate is there in soft recall and you get a broken loop somewhere on a side street, it's going to rest on the side street. I didn't do a very good job of demonstrating that, so I'm going to demonstrate it to you right now. If I go into the IO map, I'm going to turn on. We're going to go over this. Don't worry about it. If I turn on BIU number 2, I'm just recreating a broken loop here. Okay. All right. So basically I put a call in to phase 4. So now I'm demonstrating a broken loop. So now you'll see that I'm in phase 4.
Question.
Yep. Hold on one second with the question. All right. So this is what I was trying to demonstrate the other day. So when I was programming it through the controller, basically the controller was just taking the recalls and going with minimum to soft recall. Once I applied actual detection to it, so we're controlling the phase detector inputs, this is the example that I was trying to demonstrate. So 2 and 6 on soft recall, the side street loop broke, the side street loop breaks. Now that's a hard call, and now we're going to rest in the side street. So now you're driving around late at night when there's low traffic, and you're going to get stopped at the red signal because we're resting in the side street. So that's what I was trying to demonstrate why soft recall. If I would go back and put this on now, I'm going to go back and I'm going to put this on min recall. by having the main street on min recall, if I break a loop on the side street, we're at least going to toggle back and forth between main street and side street. The only difference is I'm still going to time the min on the main line, and I'm going to time the max on the side street, because the broken loop is the equivalent to a car sitting on this loop for the duration of the max time. So hopefully that makes sense. I think we have a question. What's the question?
It says, does everybody know the difference between a TS1 and a TS2?
So the question was, is everybody does not know the difference between TS1 and TS2? So I'll do that pretty quick. TS1, TS2, that's basically the evolution of the traffic signal cabinet. So TS1 is when you go to a traffic cabinet and you look in there and you have on the front of the controller, you have the 3 round connectors, A, B, and C. So you have a connector on A, B, and C, sometimes just on A if it's an old 2-phase, or A and B if it's a 4-phase. And then you have a conflict monitor. So basically you just have an A and B connected plug into that conflict monitor. In TS1, all our inputs and outputs are hardwired in the cabinet. So you look on the back panel, there's a ton of wiring, go from A to B, A to B, A to B. And every time I want to move something, if I want to change a phase on a channel or whatnot, I have to hardwire that to a different load switch position. So everything is done manually with wiring in TS1. It started out, I don't know, probably back in the 70s when we got away from electromechanicals and came over to the old L&D 8000P controllers, the old M10s. Basically, any controller that doesn't have an SDLC port on it. Okay, so that was in TS2. That was in TS1. In about in the mid 90s, we started transitioning over to TS2. And what TS2 did was it introduced the SDLC bus, the synchronous data bus. And instead of having all that wiring on the back panel, we now take all the gray cables, they're usually gray, sometimes green. We plug the controller, the MMU, and the BIUs. I should have brought one with me, I don't have one. And basically we pass all that data in TS1 that we send over hardwire. In TS2, we send it over the synchronous data bus. And it becomes a lot more easy from a programming standpoint. So now if I want to change what phase comes out of what channel, what load switch, I can just do that from programming. And before I used to have to hardwire everything. It allows you to get more troubleshooting logs, which we'll go into later. So we can generate, like when people call me up and they have a problem, I say, let's go to the alarm menu. And we go in there, we can generate frame faults, which tells us if BIUs are bad. A BIU is a bus interface unit. So that takes all the input, output, and voltage data, sends that back to the controller and the MMU. That's kind of the quick overview of TS1, TS2. We can speak to that a little bit later if you want. I don't really want to get off course with the programming. But yeah, it's important that you do have some understanding of that. This is all basically focused around TS2 because that's the standard in Massachusetts. In Rhode Island, TS2. In the northern states, it's more TS1, but it's generally a TS2 thing right now. So hopefully that answered that question. Okay, so I just wanted to re-demonstrate the soft recall and the delay. So now we'll move on to today's subject. Let me put this back. I took the liberty of pre-programming some of the stuff just to kind of make this go a little easier. Okay. So we always start at the main menu. For those that don't remember, whenever you want to get back to a main menu, I'll always tell you hit the F key. F as in Frank. F, F, F. From anywhere in the controller, you hit the F key 3 times, you're going to get back to this main menu. If we're talking over the phone and I don't know where you are in the controller, I'll simply say go F, 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 and then I'll start you from there. So that way I know what keys you're hitting. So again, we did utility data, we did phase data, we're going to do unit data today. Okay. One of the key things on this, and I'm going to keep talking about, is, so I kept my chart, I kept this part and this part. This was from last week, right? Here was our ring structure, right? Here's our layout, and then I kept the intersection, so it'll be easy to demonstrate for everybody. Two things. We have a phase, a set of red, yellow, and green intervals serving a movement, right? 5, 2, 4, 7, 1, 6. Those are phases, right? Those are phases. We can have PED phases, vehicle phases. An overlap is not considered a phase. An overlap is built of phases, okay? And then we're going to have a channel. A channel is a setting to assign a phase, PED, or overlap to. Channels and load switches go together, okay? So you'll see as we go through this that we put phase assignments, we put phases into channel assignments. They're two totally different things. So I'm going to try to demonstrate that today so we'll have a better understanding. Okay. All right. So we're just going to go through each menu like we did last week. So basically, just checking my phone as I get text in there. Okay, so some of this stuff is kind of standard. It all comes the screen comes. You'll hear me say the term defaulted. If you default the controller, these are the settings that you'll get. And generally, you'll never really touch any of these settings. I'll go through them real quick. So the startup time, the default is 6 seconds. So essentially, when I turn my controller on and off, which I'll do here, I don't want to do it here because I'm going to break the telnet connection. So basically, I'll turn the controller on and off, and down below where it says H/O, it'll come and it'll say startup, and it'll count 6 seconds. So when you reinitialize the controller, it'll take 6 seconds for the controller to actually come online. And what that's doing is that's just checking your voltages in the cabinet to make sure everything's okay. And then it'll come online and it'll go into operation. So I can change that time. Sometimes when we're troubleshooting and we're not sure what's going on, I'll drop that time to 0. And basically, as soon as I initialize the controller, it'll pop on. Sometimes we're just trying to figure out if we have what they refer to a race condition. So is the controller powering up first or is the monitor powering up first? And that's kind of a troubleshooting tool that we can use sometimes. Other than that, basically we'll always just leave that at the default. State, and again, there's all the M60s come with a big yellow help button. I'm going to use that because some of this stuff we don't use that much. I understand it. I just want to make sure I'm using the right terms. When we go to flash, typically the default is 0. If you go to 1, red assumes initialization in all red. We spoke about this last time. So typically, the way we program the flash and the controller, the main sheet will be yellow, so 2 and 6, and then all the other approaches will be red. So when we go to emergency flash, they have the yellow caution, and everybody else has the stops. We're starting to see in other parts of the country where they just make everybody flash all red. So this is a programming change that you can make if you go to an all red situation and you want it to come out in all red. And then 2 is red after flash, same as 1, but also runs all red for the program startup time after flashing operation. So again, something we don't use very often. Red revert prevents a vehicle movement from recycling back to green, yellow change, or red rest without another phase becoming active prior to this time. Again, that's intensive seconds. The example is intensive seconds /10. So basically that's 4 seconds, a function that we don't typically use. Auto ped clear, when you go into the manual control, typically you'll go in there and I can manual through the green. So when you hit the button, I can sit in green as long as I want, but then when I hit it, I have to time the yellow and then I go to the red. If I go to a walk phase, I can manual through the walk, but I can't manual through the pedestrian clearance time. If I change this setting here, that means I can force my way through that clearance time. Stop time reset. So this is basically when you come out of, when you initialize, you come out of stop time, you can have some phases time longer than others. Basically, they generally go around to their minimum time. And then we have alternate sequence and special sequence. This is used when you're reversing phases in a sequence in a ring structure that we're doing. You know, a lot of times when you do a lead lag, you could start getting into this. So typically, we're going to run 1 and 5 come up together, and then 2 and 6. In some scenarios, we'll want to go 1 and 6, 2 and 6, and then 2 and 5. We don't want these left turns to come on together. That would be something you consider a lead lag or a special sequence. You don't have to use it here, but you can basically build upon that if you have a specialized intersection. So that's just up and miscellaneous. Not too much there. Again, you don't really touch any of the programming there. Remote flash settings. So this basically, we program this if you're using something that we don't, if you're using nighttime flash. Nighttime flash used to be used back in the 80s and 90s. So basically we would, about 11 o'clock, 12 o'clock, when traffic slowed down, we would just put the intersection in flash. Flashing yellow on the main street, or referred to as soft flash. So technically the intersection is in flash, but the controller actually still runs in the background. So that way when you come out of flash, it knows where to go. So all we do here is we program, so you'll look on the top, it'll say LDSW, that stands for load switch. So whatever load switch is programmed to flash red or yellow is we'll use the code down there to go that appropriately. So 0 is dark, not being used, 1 is red, 2 is yellow. So in this situation, all our left turns are flashing red. So phase 1 would be a red, and then 2 is on Main Street. 3, 4, 5, look something like that. So that basically refers to the chart I have on the screen here. So basically 2 and 6, my Main Street, are yellow. So you can see over here, and we're doing 1 for 1. So load switch is 1 through 8, our phase is 1 through 8. So 2 and 6 are yellow, because those are my Main Street, and then everybody else is flashing red. So on all my left turns, I have 3 section, red, yellow, and green arrows. They're all wired in the cabinet to flash red. And then down here basically is, we make this alternate flash. So if you look at, say, flash on and off, 1 flash on. So basically when you come up to an intersection, I want my yellows to flash opposite of my reds. That's all that's doing there. So if you come to one of those intersections where you can kind of see the side street signals from the main street or vice versa, when my yellow is on, my red is going to be off. When my red is on, my yellow is going to be off. That's all that does right there. And then you can do that any way you want. This is Ocean State standard. We just make whatever's flashing yellow be the alternate. It's just a simple thing that we do. Okay. And then now that we have our flash settings, if we're doing nighttime flash, we have to tell the controller what phase we want it to go into flash out of and what phase we want to come out of. So typically, so standard is we enter flash in the side street and we exit flash in the main street. So again, phases 1 through 8. So I have one on entry of 4 and 8. So if, let's say we're going to flash at midnight. So when the controller goes to midnight, depending on where we are in the sequence, the next time that the controller goes to 4 and 8, the intersection will go to flash. So if we happen to, again, it's midnight, there's low traffic. If we're resting in 2 and 6, and the controller strikes midnight, we may not get a car here till like 12:15. So it's not going to go, so it's not an exact at midnight, it's once it goes to the side street. So that could fluctuate a little bit. And then the same thing when we're coming out. So when we come out, when we exit flash, we want to exit flash into 2 and 6 because that's the main line. So again, the controller's cycling in the background, even though the intersection is in flash. When the controller, let's say we come out of flash at 5 in the morning. So at 5 in the morning, the controller is now waiting for the next time it goes to 2 and 6. So it could be resting in 2 and 6. So it typically, if it's resting, it'll pop right out at 5 o'clock. If it's coming out of a side street for some reason, then it'll come out at once it gets at like 5 minutes and 30 seconds or something like that. So that's basically nighttime flash. Again, we don't use it that much, and the main reason why is because we have function detection everywhere. When we were semi-actuated or we were in pre-timed, that's when they wanted to flash because they didn't want the signals to cycle. Police enforcement would have to wait. But now that we have working detection everywhere, there's no reason to flash. Let's just leave them because they typically rest in the Main Street green anyway. So that's kind of why you don't see flash around too much. All right, so hopefully everybody gets the flash. All right, now we'll start to get into a little more of the little nitty-gritty stuff. So overlap data, all right? So this screen's a little bit different from older legacy versions, software versions in the Siemens controller. Basically, it's broken out. If you look down below, you'll see we have 4 different types of overlaps. We have the your standard overlap, which is what everybody's used to seeing. Flashing yellow arrow. I'll get into flashing yellow arrow a little bit. That's when you have the yellow arrow is flashing while you're in the main sheet of 2 and 6 or 4 and 8 is green. We have pedestrian overlaps. We covered that a little bit before. I'll get into the differences of that. And then a priority overlap, which is used when you're using transit signal priority for buses or trains. The only place we potentially could use this right now would be in Brookline. And we actually, when we first did it, we didn't have this option. So we kind of did it the other way with dummy overlaps, because that was the only way we could get it to work. Now we have an easy way. I can just turn this on and do it. So you'll see that we have 16 overlaps, A through P. We're just going to work with A here. So basically, I just hit enter, and you'll see it come up, and it'll say. So you'll see in the top left it says overlap A, and then you'll see 1 through 16. So that's phases, right? Again, phases and channels. It changes. It looks the same sometimes, because you got to understand when it's phases or channels. With the 1 through, is basically 1 through 9, and then 10, 11, 12, 13, 14, 15, 16, for those that don't realize. Okay, so basically, if I want to make an overlap, all I'm doing is 1s and 0s. 0 means nothing, 1 means make it on there. So a 1 plus 2 overlap. So I took down the other one. So typically a 1 plus 2 overlap. Get my eraser real quick. You see them more in, actually, let's do we'll do a 4 plus 5 overlap. That'll apply better to the sequence. Okay, so we have a 4 plus 5 overlap. So what that is telling us is 4 is your through, and 5 is your left turn. We can actually have movements on together for that. And what that would be is typically if you have a right turn here. So I have a right turn arrow. That's my signal right there. So what that's saying is when phase 5 is on, I can have this right turn arrow come on, because that's not a conflict, right? We would put a little jumper in the monitor to allow those 2 phases to be on. It's not saying the straight through can be on, because this is a right. So if you see the signal here, that's the signal facing over there. So this part is the overlap. This part is phase 4. Right, it's a little small to read. So I'm just overlapping the arrow part. So when phase 5 comes on, the arrow can come on. The red, yellow, and green part only can come up with 8 and with 7. Hopefully that makes sense. So that would be a standard overlap that we would use. Typically they come in with right turns and left turns. If we're using dual 2 intersections together running out of 1 controllers, a lot of times we will run overlap. So if I have 2 intersections here that are right on top of each other, like 100 feet apart, then I'll want this green to be on while this green is to be on, because we're basically running them together. So that's when we would use overlaps. So there's things that we can do with the overlaps to control how they work. So one of the most common things that we do is something called a trailing green overlap. So if I have two intersections here, basically I have a green signal here and a green signal here. When this green signal goes red, I still have 100 feet in here that I want to clear out. So basically this signal would stay on, this signal would go red, I would leave the green signal right here green for another 5 or 6 seconds, so that my vehicle traffic can flow through here and clear this middle section out. Because I want to have this clear out because I'm going to have side street traffic, and if I clear these both at the same time, the side street traffic has nowhere to go. So that's when we commonly would use something called a trailing overgraph. And the way we would do that is basically just I put 8 seconds in there, trailing green standard. That means that my overlap is now going to basically delay 8 seconds. So it's going to stay on 8 seconds longer to clear out the inside. If I'm using trailing green overlaps, I can manipulate how I want them to go. So I can do what we call a plus green or a minus green. So I can prevent the trailing green when the non-parent phase is next. One thing you'll notice in the help section, if you see a little NX with the arrows, I have 2 buttons called next and previous. If you hit that, it'll just continue on to the rest of the help menu. So I can actually omit that until this parent phase is green. So I may want to, depending on what the next phase is in that sequence, I may want to omit that overlap, omit that trailing green. We don't do it very often, but you can, it does have the ability to do that. Again, so basically this is saying, I'm going to prevent the trailing green when this non-parent phase is next. So the control is about to make a next decision. Depending on if it's going to 4 next, it may want to do something with this overlap. If it's going to 5 next, it may not care. So that's just programmable based on the sequence. And then we can also say when the non-parent is green, I want this to happen. Again, things we don't use too much. One feature that we found is we can kind of manipulate when you do, a good example is, trying to stay in the middle of the screen. I noticed I didn't do that well last time. If you do flashing signals in front of a firehouse, this is a nice way that we can basically create phasing to be flashing on and off. We create a bunch of dummy phases, and this is a nice clean way for us to get those signals to flash whenever we want them. And then when the firehouse signal comes out, basically it'll clear from 8-inch yellow to 12-inch yellow to 12-inch green, 12-inch red, and service the firehouse driveway. So that's kind of, that's actually a more common feature that we use it for. And then this one we use more often than you thought. So basically this is a minus ped, or what they used to call a not ped. So if I had a ped here, right? So I have a phase 4, and let's say that this is, a phase 4 ped. If I turn that on, what that's saying is if this overlap comes on, it omits this ped. Because that would be a conflict, giving a right turn arrow into the ped. So if somebody hits the ped button, we then can omit the overlap. So it depends what gets there first. We just did an intersection like this up in Nashville, New Hampshire. So basically when this ped is when the controller has an active ped call, we omit this green right turn arrow. When there's no ped call, the green right turn arrow comes on. So that's a safety control that we can do to kind of give it an either or. And we do use that quite a bit. So that's basically your standard overlaps. Again, I just use 4 plus 5. Depending on whatever's going on, I can make the overlap as many phases as I need to make it, depending on what I need it to do in the controller. Let me take these back out. All right. Got my help. So if I go So that was my standard, right? Flashing yellow arrow. Okay, about probably 5 years ago. I forget when flashing yellow actually came out. It was very popular. It started on the West Coast, like most things in traffic. They go West Coast to East Coast. So Washington, Oregon, I think they were the early adopters of flashing yellow arrow. And then it started moving slowly. So there's been a couple of additions of flashing yellow arrow program in the Siemens controller. About 5 years ago, 4 or 5 years ago, Mass DOT did a large scale deployment of about 300 plus intersections. They had consultants go out, evaluate the intersections, and then introduce flashing yellow arrow. So basically flashing yellow arrow, it took over for our standard doghouse signal, a protected permissive operation. Right? Everybody knows that signal. Okay. So basically in this scenario, it's for left turns. So basically we give them a green arrow here. So that's our protected movement. So that means I have a green arrow. That means I don't have any conflicting phase coming at me. And then we go to our yellow arrow. That's the clearance period. And then it goes dark. And you'll typically see a sign up on the mast arm or the span wire that'll say yield, left turn yield on green ball, something to that effect. So after the protective portion of the green, people are still free to make left turns. They have to do it basically at their own risk. They basically have to wait till no traffic comes through, and then they can take that left turn. That's considered the permitted.
The yellow flash.
What's that?
Does the yellow left turn arrow flash?
I'm getting there. Hold on. So under this situation, right? The arrows are the protect, right? And then once the arrows go out, we're just in a permitted. But the driver had no indication. All he had was a dark signal. He just had the green ball in front of him and a sign that said you could go. So it was becoming a safety concern, and what would happen is something called a yellow trap. So people keep edging out, and next thing you know, the car's in the middle of the intersection. These lights go red, side street comes up, and this guy is stuck in the middle. Very dangerous situation. So to try to alleviate that, they introduced flashing yellow arrow. Now we go to what you'll see. Everybody can see that? So here's our 4-section head that you see out there now. So basically you have your green arrow, you have 2 yellow arrows, and you have a red arrow, okay? So what happens now is when 5 comes on, right, we go to our green arrow. That's our protected movement, okay? They have the right of way. There's no conflicting phases coming out. When that times out, we go here to here to here. So we go green arrow, yellow clearance arrow, red arrow, okay? Just like it did with the other signal, all right? The difference is now, once phase 6 comes on, that guy starts flashing, hence our flashing yellow arrow. So now when the motorist pulls up, he sees a flashing yellow arrow, a flashing yellow left arrow, and it's just a better indication that basically says, okay, I can make the left turn, but that flashing yellow arrow is telling me somebody else has a opposing green signal coming at me. All right. So that's basically that's the flashing yellow arrow and how that works. So if you're driving around regularly today, you'll probably see them at least once a day. If you're a regular motorist, they have them just about everywhere. We do them quite a bit. the way we make that happen is again, you'll notice that we have the permissive phase and we have the protected phase. And the way we break this out, we're out of space. Dang. All right, I'm gonna do a little, I'm gonna leave something there. Okay. I'm gonna erase my protect and permit. I'll erase my offset. I'll put that back. I'm going to put offset back. Okay. So okay, everybody can see that. So basically, those are simulating our load switches in the cabin, okay? So load switch 1 has my green arrow, my single green arrow on it. Load switch 9 has the red, the yellow, and the yellow. The thing with flashing yellow arrow is it's a fully functioning 4-section signal. Our load switch positions, I have a load switch. If you look at our load switch, where's the front of the thing? If you look at our load switch, you'll notice that it only has red, yellow, and green. It only has 3 positions. So we have to actually use 2 load switch positions to get this thing to work properly. So we have to split it up. We have to do programming in the monitor that basically adjoins 2 load switches or channel positions together to get this to work. So what happens is we go green, this guy goes green, right? Like it normally does. But instead of having to get yellow next to it, my yellow is over here. So it would actually go to load switch 1, green, and then you would see it clear on load switch 9, yellow, load switch 9, red. And then once, I'm doing 2 and 1, I'll do it backwards. Once 2 comes on, you would then see the yellow on 9 start to flash. This is referred to as phase 1. The flashing yellow arrow part is actually an overlap. And we program it in here, and you'll see I put the permissive phase is phase 2. So what that is saying is, when this is on, this flashes. This is permissive. I'm permitted to take this left turn when phase 2 green is on. That's my permissive phase. When my green arrow is on, this is my protected phase. I'm protected. That means I don't have a conflicting 2 coming at me. Okay? And this can be used on any of the left turns. We actually have an application, I forget where we're going to do this with right turn arrows. It's our first one with the right turn arrows. We looked it all out, and it's going to work with the right turn arrows as well. So remember, here's your permissive phase. Here's your protective phase. For folks that this is the first time you're seeing it, it's a little confusing. The more you do it, the more comfortable you'll get with it. In Massachusetts, you'll notice there's this time up in the top here. That's the delay 5 seconds. So what Massachusetts wanted to do is when I clear my green, right, and I go green, yellow, yellow, they wanted to be able to control how long the delay, if any, before this flashing yellow arrow would stop working. So that's 50, actually 5 seconds. So the default was instantaneously. So basically, as soon as that went green, that started flashing. Massachusetts wanted to have a little bit of a delay in there. So we introduced that delay feature for them, and they use it accordingly. The other thing that we found after doing flashing yellow arrow is you can have some very different scenarios out there. So essentially you could have you could typically have this through movement on, this left turn movement on, and this flashing yellow arrow on. So essentially, a motorist pulls up to the intersection, and all the traffic in front of him is coming at him. So he has green straight through people coming at him, he has green left turners in front of him, but he actually has a flashing yellow arrow, and he can actually still take a permissive left turn right there. And in some intersections, that got a little hairy, that got a little confusing. So one thing that we do here at Ocean State, unless otherwise directed, is we make the permissive phase 2 and 6. So what that says is the flashing yellow arrow is only going to come on when 2 and 6 come on. It eliminates the 2 and 5 flashing yellow arrow. It was something that we kind of did on our own. If a consultant or a town wants us to take it out, we take it out. We just felt that it was a little less confusing for motorists. It was feedback we got from a class that, it was the last class we did at the Twin River Event Center. And there was a woman stood up and kind of explained the whole thing. And I knew the intersection, so I went there. Next time I was in the neighborhood, it was in District 5 somewhere. And I was watching this thing run, and I just felt like it was could be very confusing. You know, younger teenage drivers don't know what to do. Seniors maybe don't know what to do. People just don't know what to do in general. So we went back and we looked at it and we thought, you know, if you make it 2 and 6, now you eliminate that left turn through coming at me. So it's just our thing that we do. It didn't hurt in the programming. But like I said, it's always good to be optional with that. And then again, you can do your minus ped if you want to either or with the peds. And then same thing with the overlaps. So this is how we did the, I talked about the transit flashing signal. This is how we did it with dummy overlaps. This is how we had to do it because we didn't have that priority feature yet. So, but that's flashing yellow arrow. I don't know if anybody has any questions on that. I know it can be tricky for folks, but that's essentially how that works. Going to. Oh, yeah, this is just telling me I want to change the overlap. Okay, so pet overlaps. So for everybody that was there last time, you'll notice we did pet overlaps in the pet assignment screen, and you can do a pet overlap here. And here's the difference on how they work. So a pet overlap program here works just like a vehicle overlap. The difference is that it clears. You'll see that we have a walk 1 and a ped clear time. So if I do a 1 + 2 overlap, what that's saying is my phase 1 walk is going to come on, it's going to clear, so it's going to go walk, then it's going to go through the clearance, and then when 2 comes on, it's going to come back on. So you're going to go walk, clearance, and depending on the situation when we do that, we'll do that in Cambridge sometime because they use a lot of pre-time. So it's like interval programming over there. You don't mind doing it that way. And if I use a ped overlap, I'm going to use the walk and ped clear time here. And the ped, I think, did I make a note on here with the ped overlaps? No, I didn't. The ped overlaps, the biggest difference is when you do a ped overlap on your load switch, all the ped signals go under one overlap. So that's why it's treated as such. So if I have a 1 ped and a 2 ped, all the field signal wires go under one load switch position. If I do it the other way in the ped assignments, I'll go back and show you. If I do a ped, if I do that same thing here, I'll show you the most common one that we do it. If I do and we refer to this as a ped overlap, and me and Mike were talking about it yesterday. We should probably call it a ped switch, because you see where it says switch phases. If I do it this way, my 4 ped and my 9 ped are on different load switches. So like one would be on 9, one would be on 10. And what this gives the ability to do, and we do this like down in Barnstable on Main Street, is if this is my 4 ped over here, right? If I hit this ped button or this ped button, only this ped comes on, right? It becomes just like a concurrent ped. But if somebody hits this button, this button, this button, or this button, the whole exclusive ped 9 comes on and this 4 comes on. So it gives me that flexibility. If I only want this ped to come on when 4 comes on and not stop all the traffic, or when the exclusive ped gets activated, this one comes on. So those 2 ped buttons go to different inputs, ped inputs, and these other 6 ped buttons go to different inputs. And in this situation, we would have timing over here in the walk 1 and the ped 1. So this would time probably a shorter ped because it's only the side street, and the exclusive ped 9 would time another one. The one thing you got to keep in mind when you do something like this, if you're using countdown peds always display the last ped phase that it did. So we don't display the walk. I'm sorry, we display the walk and then we flash the don't walk. So if your phase 4 has a 10-second clearance and your 9 has a 20, you can display the wrong one. So you just got to be cognizant of that. Let me go back to overlaps. All right. So that's ped overlaps. Same thing with the walk 1, walk 2. Do extended push, you're gonna get the walk 2 time. And then the last one is, again, it's just that just keeps coming up because I keep changing what kind of ped it is. Again, here's the priority overlap A. This is a newer feature that we could have used, again, with the trains. And with the trains, I'll put it over here. You guys see those funky train signals they have? I believe it goes like that, like that, and like that. So you can see that's the train signal, right? That's a transit. So that's kind of like the green, the yellow, and the red. And then what happens is when the train's allowed to come through, the green, they're all white bars. The white bar comes on, but then when it goes to slow, the middle diamond, that has to flash. And this is where we can control that flash through this program right here. We can make that an overlap, and then we can kind of control that flashing output. So that's really, we could probably find another use for it, but that's the primary use for it.
Question.
What's that?
Is it possible to skip the walk turns if the ped phase overlap will come up in the next phase?
Is it possible to skip the walk clearance? Is it possible to skip the walk clearance if the ped phase overlap will come up in the next phase? The question was, is it possible to skip the walk clearance if the ped phase overlap will come up in the next phase? Yes, that's when we're going to use it. That's when we're going to program it the way I just did in kind of the switch phase like that. That's commonly how we have to use it in Boston. If we have to go to multiple phases, then we have to actually start doing it with rings, because in the switch phase, we can only do 2 phases. We only do a parent and a following. So yeah, we can do it like that. So to answer that question, if we do the traditional overlap way, it's going to clear, come on, clear, come on. If we do it the other way, that we can extend that walk. Okay. So that's that covers the overlaps. Let me clear that out. I'm not using it. I keep going to the controller because the previous and next on here. Okay, and again, we have 16 overlaps, so we can do a lot of different configurations. Okay. All right, so I actually made some notes so I could try to keep myself on point a little bit better today. Okay. All right, let me grab a quick drink. All right, one cool feature that came up. You hear us talk about occasionally is peer-to-peer. And we've been able to be very creative with this. So what peer-to-peer does is the one thing that we lost when we went from TS1 to TS2 was on the back panel, we had a lot of different inputs and outputs that we could use. Things referred to as phase-ons, phase checks, phase omecs, phase omits, things of that nature. They still reside in TS2. The problem is a back panel in TS2, we typically use, is referred to terminals and facilities, so TNF, TNF1, TNF2, or BIU1, BIU2. All those things I just mentioned are on BIUs 3 and 4. We don't normally use them, so they're not in any of the cabinets, so we didn't have access to them. They came out with this peer-to-peer option, and basically that brought all that functionality back to us. So when we used to do a lot of different relay logic, things called mutual coordination, things of that nature, we used to use a lot of this peer-to-peer functionality. We didn't call it peer-to-peer, but that's essentially what it was. So this goes back to where we start to get into a little bit of networking, okay? So the way these communicate together is you got a configure source. So each controller has to have an IP address. So you got to have an IP capable intersection. And then we have to have communication between, if you're doing multiple intersections, we have to have communication, whether it be Ethernet over serial, or we have fiber, or we have wireless. Because these guys got to be able to talk to each other. So I just put in test. I just entered that in there. So I just put in test, and I put in the IP address 192.168.1.102. That's common. And I'm going to set up a little test thing here. So I have another controller hooked up. So if I want to add that in the mix, I'll just call 192.168.1 enter, and I already programmed that for 103. So you see it's polling, it's going in there, and it's looking to find it. Okay. So now it's called fail03. I can go back and rename that in another screen just for time's sake. I'm not going to do it here. Okay. So now I got two controllers programmed in there. So you got two options at this point. So I can go in and assign functions. So I can actually I can have a controller peer to itself. So if there's some function that I want to program in, which I was doing earlier, is I simply, right, if I have multiple intersections, I can just toggle through with my next, and you'll see it'll say test or fail3 or delete, right? I want to use test because I'm peering to myself. And then my source function, that basically is the function that I want to send the command to. So what I did here is PHSGRN, that's phase green. So what's that telling me is when I'm in phase 2 green, which is what I'm in right now because I'm in 2 green, then I want to apply a min recall, and I'll change this to 1. So as I watch the controller toggle around, what I'm saying is test is my controller that I'm working on right now. When I go to phase 2 green, I want to apply a min recall to 1. So once this leaves, if I did it right, you should see an R come up under 1 where the vehicle is. Boop, there it is right there. So you go under 1, you'll see an R under the vehicle. That is a peer-to-peer function. I just made that happen through that functionality I did right there. As soon as we get our next decision to go to 4 and 8, then that recall drops off. I'm just giving you an example of the control that we have and the things that we can do. One of the things that we use commonly is I'll peer with somebody else and I'll go, right, is we like to do preemptions. So if I toggle through, you'll see all the different walks, ped clearance, whatever, and I'll get to preempt. Ooh. So you'll see where it says preempt call. Remember, when the cursor is flashing on something, you gotta hit enter. Okay. So when I get preempt call, meaning when I'm in preempt 1 in intersection in the fail 3 intersection, I want to put a preempt call in this intersection. Okay. So what this is saying, the intersection down the street, which is just called fail 3, when I put a preempt call in there, I want to put a preempt call into my controller. So you would do this with firehouse preemption. So when we used to have to run conduits and cable from the firehouse, the truck comes out, takes a left. If this is a firehouse, the truck comes out, and we want to preempt this intersection. There's a way now that we can, when this activates preempt 1 through peer-to-peer, I can preempt 2. We do this in Holyoke on the fire station on Northampton Street. They hit a button, it activates the intersection outside of the firehouse, and then preempts the next 2 intersections down. So that way they have clear way. We didn't have to run a conduit and cable. We just stuck a couple of IP radios up there, and away we go. So when I do this, down below on the screen where it says H/O, you should see preempt 1 come up. So I'll put a call in to preempt 1 over here on this controller. So all I did was I put a test call into the intersection fail 03, and that put a preempt call into my intersection. And one thing I would do is probably delay the call because it's going to take the truck 10, 20 seconds to get there. So I would put a delayed call in like 20 seconds or 10 seconds. So that way I want to ensure that that holds the whole time that it goes through. So those are just examples of how we use peer-to-peer functionality. Super simple to use. If you have intersections, you know, we'll use it. If I want to just go, when this is green, I want phase 2 green to be down there, or I want the left turn to come on, anything like that, we can, a lot of functionality through peer-to-peer. Let me just get out of this. Change some of these parameters so they don't mess me up. Okay. That's our peer-to-peer stuff. Okay, ring structure.
Question.
Yes.
Can you use peer-to-peer during coordination cycle?
You can use, yes, you can use peer-to-peer during coordination. That's it, yeah. Yes, depending on what the functionality is. Well, obviously we're limited because it depends. It depends because when we're in coordination, which we're going to talk about here pretty soon, when we're in the coordination, there's parameters that we can't get around because we're locked into, you know, if we're non-actuated, things of that way. So depending on what the application is, yes and no under coordination, because we do have some restrictions. Okay. All right, here we go. Ring structures, okay? In older legacy controllers, this was the ring structure and the phase, and the ring structure and the signal output driver was all in one, was basically on one screen. Now we've kind of broken it out a little bit, okay? So if we go back to our chart, oh, you can't see that. Hey, how are we gonna do this? All right, let me slide this over. This goes back to, slide my wake screen. Here we go. Okay. You may not see me, but this is, so we talked about our rings over here. So we're going to use a an 8-phase dual ring with a 9 exclusive ped, because that's a very common one that we use. So basically, like I said, you go, 1 is compatible with 5, 1's compatible with 6, 2 with 5, 2 with 6. And then there's a ring structure we go, it has to go circular. So it goes 1 to 2 to 9 to 3 to 4, and then back to 1 again. All right? 2 and 6 have to cross the barrier at the same time when it goes to 9. 9 by itself has to end before we go to 3 and 7. Right? So how we build this is right here in the ring structure. So basically you'll see up top, lose my telnet session here. All right. Hold on, I think we may have lost our telnet session. All right, I'll just do it this way. All right. All right, so you notice at the top where it says ring structure, phase 1, ring 1, next phase 2. So all that is saying is, if you look at my picture over here, ring 1, so you'll say phase 1, ring 1, 2 is next. And then where it says compatible phases, it's compatible with 5 and 6. So this right here is being brought out in that screen. So phase 1, ring 1, 2 is next, and it's compatible with 5 and 6. Okay? And we just toggle down through, and it keeps going. So we're saying phase 2, ring 1. In this situation, we're going to add in phase 9. So this was part of the program that I wanted to do. Okay? So what we would have to do is hit enter, and then we want 9 next. So we hit 9, enter. And again, we have the cursor flashing. So to get rid of the cursor, we hit enter. And then we're going to toggle down where it says phase 9. We hit enter. If you notice, 9 is not in the ring structure right now. Ring nothing, phase nothing, because it wasn't defaulted in there. So what we're going to do is go enter, ring 1, 3 next. In compatibility, it has an X under the 9 because it's only compatible with itself. So then we'll just hit the enter, and then we'll go back up. So now you got phase 2, ring 1, 9 next, compatible with 5 and 6. We'll go to phase 3. Phase 3, ring 1, 4 is next, compatible with 7 and 8, because 3 can be on 7 and 8. And then 4, phase 4, ring 1, compatible with 7 and 8, same thing. And if you look where it says the next phase, you'll notice it says 1, because it's going to go back to the beginning of the ring again. And then we'll proceed down to ring 2. So we have phase 5, ring 2, compatible with 1 and 2, and 6 is next. So it just kind of steps you through how the whole thing goes. Same thing. 6, ring 2, compatible with 1 and 2. And that compatibility, just a reflection, so 6 can be on with 1, 6 can be on with 2. 6 can be on with 1, 6 can be on with 2, because that's my arrow from before. 7 to 8, and again with 8, 8's on, ring 2, and you notice it says 5 next. So now the 8's going to go back to the 5, just like the 4 had to go back to the 1. And then the 9 that we had in there, the 9 went to 3 next. Okay? When you're all done with it, if you did it right, you hit the F key, you'll get these 3 messages. It'll say A to abort with no change. C to initialize, Alt sequence, we're not using that, or E to accept and exit. You want to always hit E. That means you did it right. If you did it wrong, you would have A and B. A would be to abort no G, B would be to back up because you made a mistake, so you don't have to redo the whole thing. So if I hit E, when I make a change to a ring structure, you'll know there's that stop flash down there. It's going to cycle power my controller, okay? One thing people get confused with when we add 9 is we have to put it in the ring structure before we can turn it on. So now we would go back to our phase data, and we would have to put it in the ring structure. So we go 3, we go back into our initialization. This is the screen that we had before. And you notice under phase 9, we have a 0, we're going to make that a 1. And again, when I turn phases on and off, you'll see the start flash going. That's that 6 seconds timing down. So now my 9 is in the ring structure, okay? I'm going to go put timing in 9. If I go to 3 for ped times, I'm going to scroll over. All right, so I already get time in there, that's fine. I must have put that in there before, okay? All right, so I just built the ring structure and I added in my phase 9. So if we look at our intersection, let me slide this back over a little bit more for everybody. We go back in, so my ring structure over here, get my big head out of the way, 1, 5, 2, 6, 9, 3, 7, 8 is 1 and 5, 2 and 6, 9 the exclusive ped, 3 and 7, and then 4 and 8. So we just built a standard ring structure that you see very commonly in Massachusetts. And around New England, this is a very common one that we use. So now that we have a ring structure, all right, now we're going to put it somewhere. So now we take our ring structure. Now we have to assign it to our output mapping. So basically in this screen, I'm going to go back to those other ones, but these screens tie directly together. So again, I talk about doing the default, right? When you do the default, basically it assigns it up the top. Oops. Go back. All right. You'll see across the top, it'll say LDSW. That's load switch. And that's basically 1 through, it goes I think to like 24. And then you have phase 1, then you have red, yellow, and green, and FIO. FIO is field input output. So the default is we assign phase 1 to load switch 1. We always try to keep it lined up. I'll get into how we can reprogram it all over the place, but ideally this is where you want to keep it together. You want to keep it consistent, so that way when somebody comes to the cabinet afterwards, and typically there's no documentation, I most commonly can look down and say, okay, the load switch is starting from the left, they're going to be phase 1. So it's kind of consistency between all the cabinets. So if I go phase 1, phase 2, phase 3, phase 4, phase 5, phase 6, so I get the 8 phases in, and then you notice I do my 4 even peds, 2, 4, 6, and 8. And then I go to my overlaps, A, B, C, and D. I know there's 16, but we standardize on these 4. I can use the other ones, but these are just part of the default. And then I have my 4 odd peds, because these are they're less used than my even peds. Okay? And this goes back to that TS1, TS2 controller. In a TS1 controller, when I default this is what it comes up on. I can essentially go back. I can go back to the screen and just turn phases on and off. I think I showed you this a little bit. And pretty much get the intersection to run because of that default programming there, right? Because everything is, remember, everything is hardwired on the back panel in TS1. So a lot of my program just stays the same. We don't have to manipulate it. We go into TS2, this is where we have to start making changes. I go back into my output mapping now. Let me stay with TS1 right now. TS1, this is where my field input output becomes a little more critical, because everything is hardwired on the back panel between a load switch from the inputs to the outputs. Where it gets a little dicey is typically with our PEDs. The default in a lot of cabinets is they'll put the jumpers on that basically wire. If you look on the back panel, it'll be hardwired phase 2 PED to load switch 9, phase 4 PED to load switch 10, like it shows right here. But what if I'm using a 9? If I'm using a 9 PED, right? So now I have a 9 PED like I have in my ring structure. That's fine. So now I want the 9 PED to come on load switch 9. That's fine. What we have to do is we have to line up the field input output drivers. So on the back panel, if load switch 9 is wired to phase 2 PED, that's fine. I can leave it there because 9 is associated with phase 2 PED. A lot of times what they used to do is wire, before we had 4-ring machines, phase 3 PED was always our exclusive PED. So we would wire the load switch to PED 3 inputs. So if we did that here, if you look at PED 3, PD3, you'll see the FIO is 18. If that's what my cabinet looked like there, I'd have to change that to 18. If I didn't change it to 18, I get a red fail because I would have a load switch that was dark, conflict monitor wired to the load switch, trying to look for the programming of, trying to find the voltage of it, and it doesn't see it because it's not assigned there. So in TS1, our FIO has to match however our back panel wiring is. I know that's a lot to understand, but essentially it comes into PEDs and overlaps because those are the ones that fluctuate on load switches 9, 10, 11, and 12. So if you're going to reprogram something and you can't get a PED and the load switch is dark, go look, find the wires on 9, follow which PED they're going to, and then put that FIO number in there to match, and I guarantee it's going to start working. So hopefully that makes sense. The more you do it, you might want to rewatch this a few times, but basically your FIO has to match how your back panel wiring is done. And that's a TS1 thing. So if I actually hit the help screen here, it tells me FIO provides routing between SDLC load switch number and the FIO load switch number. FIO remapping applies to TS1 and 2070 outputs, primarily used in TS2 Type 2 cabinet. So it primarily applies there because that's where we have the hardwire. Like in Boston, we use TS2, that's a hardwired back panel. TS1 is a hardwired back panel. TS2, we do it through the SDLC as it mentions in the top slide. All right. Now, if we're in TS2, which is where we got our BIUs, our SDLC, all that stuff. Now the way I have to do this is any unused phased, this is probably going to go to flash. I basically, if I'm only using 2, 4, 6, and 8, I actually have to turn off the unused phases. So now, assuming that I have a 12 position back panel, right? Sorry, I go a little back and forth here. If I don't have any left-hand turns and I just have all my throughs, 2, 4, 6, and 8 with 9, in TS2, I would turn off all my odds and just leave on my ones. And technically, I could zero all this out because I'm doing it. I'm not going to go through it just for time's sake, but. So in TS2, because I can do my programming, because everything is going from those BIUs on the back panel through that SDLC cable back to the control and the monitor. There are no wires on the back panel to do this. That is in the TS1. In TS2, it all gets done through that BIUs and the SDLC, which I'm going to go into that. Let me just put this back. Bear with me with 2 seconds. Bear with me, bear with me. All right, I don't think that's gonna. I'm just gonna leave it like that just for the sake of time. Okay, so that's so that's our output mapping. In older legacy controllers, this used to be on one screen. It was still under the 9 screen. You would see the signal driver outputs on the right. You would see the phasing channel on the left, and it would kind of go from one side to the other. So they broke it out so we can have a little bit more flexibility doing it this way. The other cool thing too is if you hit the E, that kind of brings up red, yellow, and green. So we've done this a few times. So you notice in 9, I have PED 9, the clearance output. So when you tie the signal wires on there, I'm actually not using this. This is actually a spear. We've done some flashing yellow arrows where we've actually used this and changed that to a signal driver, so we could use that as our green arrow for a flashing yellow arrow. So it just allows us more flexibility because we can break out the red, yellow, and green. If you have a 12-position back panel and you need to add something, we can be a little flexible to use unused outputs to do other things. So that was a big benefit to that. So that's the output mapping. I've talked a lot about TS1 and TS2. Here's the main part of TS2. So here's where we're saying the TNF, terminal facilities, BIU number 1, TS2, right? On the back panel, you have 2 BIUs. We refer to TS2, BIU1, BIU2, upper BIU, lower BIU. And the if there's 12 load switch positions, the upper BIU does load switches 1 through 8. The lower BIU does 9 through 12. If it's a 16 position back panel, the lower BIU does 9 through 16. So depending on where your failure is, if you have a failure on 1 through 8, we're going to be looking at that BIU number 1. If it's 9 or later, we're looking at BIU number 2. And that tells us, when we cover the alarm part, when we go into the frame faults, it associates and tells us a specific frame fault directed to that BIU. So the way we do it is we just want to turn these on. So instantly you saw down the bottom, cabinet diagnostic flash. So I'm going from a TS1 format to a TS2, but that's okay, so I just want to show you. So again, you see BIU 3 and 4, those are the ones that we hardly hit, that are never in cabinets, that have all that unused stuff that we now use in peer-to-peer. We have detector BIUs. So we have a detector rack, that has a BIU in it. Some cabinets have 2 detector racks. If it has 2, you have to turn on the second BIU. And 3 and 4 BIUs, right? So we have 4 back panel BIUs, 4 detector BIUs. And the 4 detector BIUs are broken into detector channel assignments. So each one has 16 channels on it for a total of 64. So detector BIU 1 does 1 through 16. Detector BIU 2 does 17 through 32, and so on. Those of you that are involved, that work with adaptive signal systems, you say, wow, so who's going to use 60-foot channels of detection? In the adaptive world, you use quite a few of them because you have so many of those loops and zones out there. And then we scroll down, and the other two things we turn on are the MMU and the controller. So in a TS2 cabinet, there's a hub assembly with five wired connectors on it. And basically, they all plug into the RS-485 port, the one on the controller, the one on the MMU, and on the 3 BIUs, they all plug in. And that's how those communicate back and forth. Basically, the controller and the MMU, they're sending out commands. They're basically they're checking for voltages, they're checking for inputs and outputs, detector calls, and then they want what they call responses back, frame responses. If it doesn't get a frame response back in 3 tries, it'll register a frame fault. Some frame faults are due to programming, some frame faults are due to voltages. Depending on what they are, it'll cause the intersection to go to flash. That's why we ask you to go, when we're troubleshooting, to go to the alarms menu, and that'll try to pinpoint us where we're going, what frame fault, what piece of hardware we're going to have trouble with. TS2, super easy for programming. It makes things much more flexible, very device heavy. We burn up devices. If you don't have a replacement device, MMU, BIU, you're not going to get the intersection going. In TS1, where everything is hardwired, if we burn something up, we can generally hardwire around it. So there's definitely pros and cons to both. We're not going back to TS2. We're not going back to TS1. We're TS2. If anything, we're going forward to ATC, which is even more, less wires, more devices. So that's why it gets a little challenging for agencies to have spare equipment on hand. That's why I always stress anytime you guys can scoop up replacement controller parts, don't ever throw anything away, but always know what is good and what is not. Because there's nothing worse than troubleshooting with bad equipment. That just makes the problem that much harder for you and for me. In a TS2 cabinet, one thing you do have is the BIU and the detector rack essentially is a spare BIU. So if you blow out BIU number 1 on the back panel, you can use the BIU and detector rack in the detector rack to get the intersection going. The only downside is the intersection will be on recall, but at least you'll be back in operational colors. The most important thing is to get us back in colors. We'll deal with recalls another time. So you just have to get another BIU in there. So essentially, you always have a spare BIU in the rack that you can use. If you have a bad one down below, don't stick it back in the rack. Basically, you're going to get rid of it. They're not even repairable anymore. They're kind of like a throwaway device, like a load switch, unfortunately. But it is what it is. So that's the that's the ring structure, the output mapping, and the port I/O. Hopefully that that was a lot to digest. Go back through this video, and the more you listen to it, the more I think it'll make sense to you. Is there a question?
Is there a big difference in the BIU 100, 200, or 700?
So the question was, is there a difference between BIUs 100, 200, and 700? The answer is no. So every manufacturer, cabinet manufacturer, could have their own BIU device that they make, so it has a different model number. So Siemens used to have BIU 100s, and then they end up with BIU 200s, and now we've gone to using EDI makes a BIU called a 700. They're all interchangeable. They all do the same thing. Some cost a little more than other. Some have a little bit more suppression on them or other, but they all kind of can do the same thing. The BIUs are interchangeable between controller cabinet manufacturers for the most part. I'm not going to tell you 100% of the time if you put a Peak BIU in a Siemens controller, it's going to work, or on Siemens and a Nasdaq, it's going to work. They're all supposed to be the same, but I would tell you 98% of the time it'll work. The 2% of the time it's not going to work. There's probably tolerances on that device that just aren't working, that aren't compatible in that other controller. Same thing with the SDLC cables. Some cables are pinned out all the way. The ones that have a full complement of pins in the connector are the ones that tend to work better. Siemens does a really good job where if you look in a cabinet, you'll see where the 5 harnesses connect to a hub assembly, and some manufacturers take the other end and put it on a termination block. The problem with the termination block is there's 8 wires that you need in there. And so 8 times 5 is 40. That's 40 more termination points in a cabinet that you don't need, 40 more potential chances for failure. We sell a lot of hub assemblies and SDLC cables that agencies put in other manufacturers' cabinets for that one reason. It was just a really good concept that they came up with. Not everybody does it. A lot of people have gone to the hub assembly. We've just always had it. Well, early on we didn't, and then we found the ills of it in our ways, so they changed it to the hub assembly. So if you're having SDLC problems, because there's nothing worse than chasing down SDLC problems. I know agencies that just keep a spare hub assembly and they'll just stick it in there. And if that gets the thing running, then they know they're just going to change it all out. Because a bad BAU or a bad cable it'll make you pull your hair out of your head if you're not sure what you're doing. So just to kind of keep that in mind. That kind of covers, unfortunately that went longer than I thought. I mean, this is the way these classes go. I'm trying to be very deliberate and slow because we have a lot of new people on here. We do have about 20 minutes left. I'm going to just start a little bit of the coordination just to expose it to you, and then we'll finish it off on the next week because I don't have enough time. I can't get through it in 20 minutes. But I'll spend it on the coordination thing, and then we'll get to programming in the controller next time around. So if nobody else has any more questions on the unit data stuff, I'll move on to, because I got the coordination stuff on here anyway. So any more questions?
Yeah.
Okay. So in coordination, basically there's 3 terms that you're going to be familiar with. Cycle or cycle length, split, maybe erase my offset. And offset. And commonly you'll see in the controller, it'll say C/S/O. So cycle split and offset. Sometimes you'll see dial split and offset. So dial / but it's the same dial cycle, same thing. So I'm going to make this a very basic coordination class because we can do all day on the coordination. But just so you guys understand, so when we're putting the programming data in, these will make sense. So basically in coordination, here's your CSO, you have a cycle length. The cycle length for this practice is going to be 100 seconds. And what that means is I have to service all my phases in 100 seconds. The 100-second cycle length is broken down into splits. Okay? A split applies to phase time. So for this example, well, let me look over here. Split is calculated by the red, the yellow, and the green time. All right, I'm using 15 seconds of green as the max, but typically we only have to consider our minimum time. So for argument's sake, we're going to say that the minimum green time is 15. So it has to be the sum total of these 3. So if you look at it, 15 plus 3 plus 2 is 20. My split is 20 seconds. Okay? If I go on to phases 2 and 6, I have a min green with 24, plus 3 for yellow, 2 for red. That equals 30. My split is 30 seconds. And then we do 3 and 7, same thing. 4 and 8, same thing. So we now add up 20 plus 30 is 50, plus 20 is 70, plus 30 is 100. That's how we created our 100-second cycle length. If we input these values the right way, we will now service every phase accordingly. If I made this 15 seconds, which is not the sum total, it's less than the sum total of that, I would get a bad coordination plan, and I wouldn't run the cycle program. So every split has to be greater than, equal or greater than the red, yellow, and green time. I didn't include the ped time, but if I had a ped time in here, I would have to accommodate the ped time also. So the ped time would be the walk, the clearance, and the red time. So for 9, if my timing was 5:15 and 3 seconds of red, 5 plus 15 is 20, 3 seconds of red is 23, my 9 split would have to be 23. Now you're saying, how do I get 23 seconds in here? This is the kicker. I have to fit 23 seconds in here, which means I got to take time from everybody else to be able to fit it in there. I say all the time, three quarters of the problem, 3/4 of the challenge in coordination is cycling all your phases. Once you can cycle all your phases, then it's just fine tuning after that. The other term that you have is an offset, right? We did the cycle, we did the split, and now the offset. The offset is basically, when I have 2 intersections, is how long it takes for the platoon, the cars, or the platoon, or the queue it's referred to get from intersection 1 to intersection 2. What that means, I don't want to start a green here, and here, and here, because if everybody starts on green, by the time I get to the 3rd intersection, the green would have timed out already. So I want to, based on distance and speed, if I start this one at 0, I want to offset intersection 2 by, let's say, 10 seconds and start the green down here. So this way, so when you drive an arterial, ideally, you should get a green light, and as you start driving, sequentially, the other intersections go green, go green, go green. That allows your queue or your platoon to go the whole corridor at 35 miles an hour, whatever the speed is, and make it. If I see everybody go green at the same time, I'm probably not going to get to the 3rd intersection, and it's going to go red, and they're going to start servicing side street. So basically, we have cycle lengths of 100. I just made it simple. Our splits are 20, 30, 20, 30, which added up equals 100. And then I have a 10-second offset. Those are the 3 main things of coordination. If you put any of that in, it'll run your intersection in coordination, assuming that you have your well, that'll run in time base. If you have any communications and whatnot, right, that'll run the intersection. So when you guys change out controllers, it's not hard to input this coordination information back in there. It may not run perfectly. You may have a little bit, this left turn may only get a couple of cars, so 20 seconds is probably too much. So this is where you would say, okay, I can make this, if my min green was only 5 seconds, right? My min green was only 5 seconds. 5 plus 3 is 8, plus 2 is 10. This is a quirky thing in a Siemens controller. I can't go less than 11. I can make that 11. So instead of 20, I made it 11. I could then just add 9 seconds to the main street. So my main street could then go to 39. Right? So where 20 and 30 used to add up to 50, now 39 and 11 add up to 50. So that's how we can manipulate the split time based on our traffic demand. Right? That's all, consultants use different software, Synchro, to calculate this. You can go out there and basically know how many cars are coming out. It's typically 2 cars a second. And you can figure that out and just kind of put in a poor man's coordination plan just to get some coordination working. A lot of times with the offset, we'll just sit there with a stopwatch and see how long it takes to get from intersection 1 to intersection 2 and kind of manipulate it that way. But that kind of just goes over the cycle split and offset. Again, there are minimums. When you go into tactics, the management software that we talked about before for Siemens, in that screen, it'll basically tell you in the coordination plan that you have what the minimum has to be. So it'll go along and say, okay, the minimum of one has to be 11, the minimum of two has to be 15. I can make it greater than that, but it'll tell me what I can't violate these minimums. So what happens, a perfect example is, there'll be a nice coordination plan in there, running great, and then you guys, because you don't know, but this is when I yell at you. So the coordination timing is set up, so if you look at phase one, I have 5, 3, and 2, like I have up there. So what'll happen is, the loops will break, nobody's getting called, so what you'll do is you'll go like this, 15, boom. So right now, you just violated my coordination plan, because now my split is now 15 plus 3 plus 2 is 20 seconds. If I go back to my chart, which I don't have, well, my chart was 11. So now you violated my minimum because you added 15 seconds over there. What I would rather have you do is add the 15 seconds here. So now I maintain my 5 and my 15, my 5, 3, and 2, and you just bumped up the max, all right? Now, at this point, I would put time back into the split. I would take it from somewhere to get more time to phase one, but that's a better way to do it. A lot of times everybody just comes in and they sit there and they just max out. They go right across the board and make all my min green times 20, and then it just violated everything in my coordination cycle. So that's kind of just a kind of introductory to coordination. Again, I'll cover how to implement all this timing into the controller. Just to kind of give you an idea. So like this would be your split times. This is where we would go in and implement all those timings in there. You know, this would be your, if we went by what I was just doing, the orange, you know, it would look something like this. It's not allowing me to enter it because I've already done violations, but basically it would go into those I'd have to go through some of this setup first before we can get into that. So but like I said, I just had extra 10 minutes to do this. But that's general coordination. If you can understand that, you just learned a lot about coordination. There's a whole bunch of other stuff where you do fine tuning and specifics for specific intersections. That's where it kind of goes off the rails, as they say. But if you can understand that general premise of coordination, then you're doing pretty good, and you can get an intersection to operate coordinated. So when you change out controllers, it's not hard to get this information back in there. Even if it's not specific, it just has to be close, and you can get it back up and running. So, but that's basically all I got today. Like I said, it's already 10 of 12. I don't know if you have any more questions. Again, we're recording this, so you can go watch them later. Again, they're going a little longer. COVID-19, who knows how long it's going to last for. So I think we have enough time to cover everything that we want to cover. But other than that, like I said, it's recorded. You guys want to go back and check it, feel free to check it. I know there's a lot of guys couldn't log in today. They're gonna check it later. And then we'll just carry on. Same thing next Tuesday, about 10 to 12. We'll start with the coordination, and we'll do time based. We should be able to combine both of those together, because the coordination, doing this part to implementing the data, doesn't go that quick. So we should be able to catch up next week. Again, I want to thank everybody for their time today. Good class. We still had about 15 people log in. I know there's multiple people logging in, so as long as it's worthwhile for you guys, we'll keep doing them. And if you have any more questions, send them to me afterward, and we can go from there. Just checking. But that's about it. And you guys have a great week. Enjoy the rest of the week, and we'll see you next week. All right. Thank you. Take care.